So, Chapter 5 Gases, Take 2. Apparently the first one I made of this had a lot of mistakes in it. It had 3 of the problems had mistakes. So I fixed them and hopefully we've gotten everything right now. So now that I've wasted 16 seconds of your time, we'll continue. Section 5.1, examples and background. Oh, examples of gases and background of gases. So you need to know gases take the shape of their container. Unlike solids, where solids just sit at the bottom of their container, liquids take the shape of the bottom of their container, but they don't fill the entire container, whereas gases will fill the entire container. Now this is very important, this Hofbrinkel thing here. You have to memorize this. This is not only about gases, but most of these are gases. Everything except for iodine and bromine in this list is a gas. So these elements, HOF, bromine, iodine, nitrogen, chlorine, are all diatomic when they're pure elements at 25 Celsius. And we write them as these diatomics right here. So whenever I say hydrogen gas, you need to visualize it's H2, not just H alone. This will come up a lot in the problems. Oh, also, the gas phase is the most compressible state of matter. That means it can be smushed down. If you take a liquid, you can't really push it into a smaller volume, whereas gases can be compressed into smaller volumes. 5.2, gas pressure. Pressure that gases cause, they're caused by gas particles hitting the walls of their container, and it's a force. As the number of collisions of the molecules and or the force of the collisions increase, pressure will also increase. So when a particle hits its container walls, it creates a force on that wall. The more particles there are, the bigger the force. And if the particle hits faster, it means it'll be hitting with more force. So the pressure would go up. Here are your units for pressure. Atmospheres, torr, millimeters of mercury, literally millimeters of the element mercury. You'll see a little later how that comes up. Kilopascals and pounds per square inch. These are the abbreviations. When you see those abbreviations, you should read it as the whole word. So we don't say 1 ATM, we would say 1 atmosphere. So copy those down. You might need to pause. Okay, measuring pressure. We can use a manometer or a barometer. I'm going to show you manometers, and you should notice that this manometer right here is a closed manometer. That piece right here is closed off, whereas this one is open. That's an open manometer. Those are both open manometers. Okay. In the closed manometer, oops, wait, let's move this down a little bit. Okay, there we go. In the closed manometer, we have the gas pushing down, and this brown or black area is literally the element mercury. Well, not literally because you're looking at a video, but if this was a real manometer, we would have mercury in here. And up in the top of a closed manometer, we have a vacuum, meaning there's no pressure, zero pressure up here, no gas molecules, nothing. We have the mercury between here and here, and the gas is pushing on the mercury and pushing the mercury up toward the vacuum. So if we look at this and we say which side is pushing more strongly, this side here or this side here, we see the gas is pushing lower than the vacuum is pushing. So the difference between these two, that would be your millimeters of mercury. You measure your distance in millimeters of mercury. And the pressure of the gas would be the height difference in millimeters of mercury. In the second one, we have an open container. And again, we have our black grayish mercury here. From here to here is the difference between the air outside pressure pushing down on this manometer tube, whereas the gas pressure is pushing over on this side, on this end of the mercury. And the gas pressure would be the outside pressure, because that's pushing down on here. And will the gas be bigger or smaller than the atmospheric pressure? I'm going to think about that. Bigger or smaller? Who's pushing harder, the gas or the atmosphere? Let's see. Hopefully you got that right. The gas is pushing harder because we see the gas pushes lower than the outside atmospheric pressure. So the gas pressure would be the atmospheric pressure plus this height in millimeters of mercury right here, this H2 right here. Okay, the third one. Notice this time the atmosphere is pushing harder. The mercury level is lower on this right side than on the left side. So on this system, the gas is lower or higher than the outside? It's lower. So the gas pressure is the atmospheric pressure minus the height difference because the atmosphere is pushing harder. Okay, let's do some conversions. To do gas conversions, we just use these. We can convert directly from any of these to any other. I don't have to, if I have a question for PSI to millimeters mercury, oops, I said actually PSI, we do say PSI as opposed to pounds per square inch. That's one exception to reading these out loud. In any event, if we're converting from PSI to torr, we can go straight 14.7 and 760. We don't have to convert to kilopascals, then to millimeters mercury, and then to torr. So you might be able to do this on your own. Here's your solution. You start with your given, and we look at the conversion factor. If you look back up top, 760 millimeters mercury is equal to 1 atmosphere. So that would be 0.034 atmospheres. Pause this, try this next one on your own, and here's your solution. There you have it. Why did I keep only 3 digits? Sig figs. A lot of you are having trouble with sig figs. There were only 3 sig figs in the question, so I keep 3 sig figs in the answer. Okay, moving on, gas laws. So, the first law we're going to look at is called Boyle's law. It's important, well, I won't test you on this, but lots of people think it's important to know that Boyle's law is the relationship between pressure and volume. You do need to know that pressure and volume are inversely proportional. That is the important piece of information. Pressure and volume are inversely proportional. Boyle happens to be the one that developed this law. Next law is Charles' law. Charles' law talks about volume versus temperature, and you can use Charles' law to find what absolute zero is. You don't even know about absolute zero. I'll talk about that once I open this little box up. So there's something called Kelvin temperature, and your Kelvin temperature is your Celsius plus 273. Absolute zero is the coldest possible temperature. We cannot go below 0 Kelvin. There's no such thing as a negative Kelvin temperature. And we can use Charles' law to actually find out what we can extrapolate down to absolute zero. We can't actually get there. No one has. We've gotten very close, but not actually absolute zero. And what you do is you plot volume versus temperature in Kelvin units, and then you extrapolate down to zero volume, and that gives you absolute zero temperature. Okay, last one for now, Avogadro's law. Avogadro's law says that volume and moles are directly proportional. So volume is a constant times moles. Now the important things here are not who wrote the laws over on the left side, but rather on remembering and knowing whether 2 variables are inversely or directly proportional. And actually you don't have to remember each one separately, you just have to memorize this right here. The ideal gas law. If we combine those 3 laws, we get what's called the ideal gas law. All of your variables are defined right here. And again, I'm having you fill in this conversion from Kelvin to Celsius. This is a very important conversion that you will need to know. You'll have to use it very often throughout the whole school year. Okay. Now what is this R thing? It is called the universal gas constant. It's 0.0821 atmospheres liters per mole Kelvin. It has all these units in it. It's like velocity. You'd think of velocity as meters per second. Maybe you don't know about that yet. But we could talk about, I'm sure you've heard of miles per hour, how fast you're going in a car. There are 2 units in velocity. Well, in the gas constant, we actually have 4 different units combining to make one whole unit. All right, some problems. I didn't mean to erase the top. There we go. Okay, you have that one printed out already. What mass of nitrogen gas is in 2.5 liters? Blah, 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 blah. Okay, let's identify all of our variables first. So we've got our kilopascals, that's our pressure, And because R is in the units, has the units of atmospheres, we're going to put our pressure into atmospheres. Now, what other units are we given? Let's see. We've got a temperature right here. So now we've dealt with pressure and temperature. We convert our temperature to Kelvin. We have to always do that. And then we have this last unit right here, our volume, 2.5 liters. So we've got a pressure, a temperature, and a volume. And we're looking for mass. We want to find mass. So you should recognize with the ideal gas law, we can find N from the ideal gas law. And then we can always convert moles to grams. That's easy. You should know that by now using molar mass. Here is the solution. This is one of the mistakes I had earlier. I had 15 here, but it's actually 1.5 grams of N2. Okay. You should try this one on your own, but I'm going to go ahead and work through it for you. So you want to identify your variables. First, we are given this grams of O2. Let's see, we had the grams of O2. And we're thinking about gas laws because we've got a pressure unit over here. So you think gas laws, I need moles. So we convert this to moles. Then we've got our milliliters. That should give us a volume, but we're going to have to convert that to liters. Let me show you why. The gas constant has liters, not milliliters. So we're going to have to convert our volume to liters. So pressure always in atmospheres, volume in liters. Okay, so 25 liters. And then we've got, we still have, oops, I don't want to move that. We have a pressure unit over here, and we will have to convert that to atmospheres. You can't see the number I have. Okay, we can plug that into the ideal gas law now because we have moles, volume, and pressure. By the way, I didn't mention the last problem. Always isolate the unknown variable and then plug in your values. So I'll show you what I mean here. So we want to find temperature. And notice I don't write out PV equals nRT, I isolate T. So T, if we isolate T in the PV equals nRT equation, we get T as PV over nR. Now I plug everything in, and we get 298 Kelvin. Okay. There's something called a two-state problem. In a two-state problem, the gas is at one set of conditions, and then it moves to another. Gas is at one set of conditions and goes to a new set of conditions. And you'll know these problems because you will see N, actually not N, you'll see P, V, or T, and or T listed twice. So this twice here, twice, two-state. If you see something twice, you know you have a two-state problem. Okay, so here we have a temperature of volume and another volume, and we're asked about temperature. Notice it mentions pressure, but pressure is not in the problem. There's no pressure units here. You're told pressure is constant. You know it's a two-state problem because volume and temperature are listed twice. Here's temperature the second time. So first you're going to identify all your variables, 25 Celsius. You read this to figure out which one is your ones and your twos for your conditions. So the gas is at 25 Celsius in 2.5 liters. That's where we're starting. That's where we're at. So that's why it's T1. Always Kelvin. You cannot use Celsius ever in the ideal gas law. One state or two state problems. One state was what we just did earlier with the stoichiometry. Okay. Oh, we didn't do sorry. One state is these problems. What temperature? We'll be learning stoichiometry next time with gases. So these are one state problems, the original ones we did. Okay, back to this problem. So 2.5 liters, that would be our volume initial. Now what do you think this volume is? We increase the volume to a new set of conditions. That means that that's our second volume. So we've got V2, and we're trying to find T2. So here's how you solve these problems. You write out PV equals nRT, and you underline the variables in the problem. You can't see this because of the red lines, but the V and the T are underlined. So you want to write out these directions. You will need them. So underline the V because we have volume in this problem. You underline the T because we have temperature in this problem. You rewrite the ideal gas law with only the variables used. So we will write V equals T, and then you put a subscript 2 on the variables. So you'll actually write V2 equals T2. This is the part that seems really weird to students. You divide by the same variables and write a subscript 1 on the denominator variables. Now I'll show you what this looks like. It's not so complicated. You just write, oops, V2 equals T2, and then you divide by V1 and T1. So no matter what the variables are, wherever they are in this equation, you write them on the correct side of the equal sign. You put 2's on top, 1's on the bottom, and it makes it really easy if you just do it this way. You don't have to memorize any of the Boyle's law, Charles' law, or Avogadro's laws. You just use the ideal gas law and do this procedure. Okay, now we are trying to solve for T2, so I'm going to isolate T2 in this equation. So we're going to isolate T2, isolate the unknown. Should always do these in these problems. So isolating the unknown, T2, so T2 will equal V2 over V1, and then T1 comes to the other side. So V2 T1 over V1, we plug in the values from up here, and we get our answer. Now, the most common mistake people make here is putting your volumes or your temperatures, mixing up your 1's and your 2's, putting them in the wrong place. So you have to go very slowly on these problems to make sure that you are doing them correctly. Okay, last problem. Here's your problem. We've got a volume. You have to start recognizing your pressure units. So we've got a volume, a pressure unit, and a new pressure unit. Temperature is constant. What's the new volume? So the wording tells you you've got a two-state problem. So what's our first step? Oh, by the way, solve this on your own if you want. You don't need to watch me. You should pause this actually and try it on your own. In any event, back to the question at hand. This is a what kind of problem? A two-state problem. I'm sure you got that right. It's not a one-state, it's a two-state. So what do? We write PV equals nRT, and we underline, oh, no, sorry. First, we identify all of our variables. So 250 mils. The gas is in 250 mils at 765 millimeters mercury, not mmHg. Remember to read that as millimeters mercury. And that would be our initial volume because that's what the gas, it's at these conditions, and then we increase the pressure to get a new set of conditions. So 250 mils is our V1, 765 millimeters mercury is our P2. Now, just ignore this part, actually, hang on, ignore that part for a moment. We're going to go this way. Okay. No, we'll just leave that up there. The pressures are in different units. So I've got kilopascals and millimeters mercury. I don't have to convert these both to atmospheres. I just have to make sure that they are in the same units. So I just chose to convert this millimeters mercury into kilopascals, and then the other pressure I will leave as kilopascals. Okay, so there is our P1 right here. And then this other pressure would be our P2. There we go. Remember, we write out PV equals nRT, and we underline the variables we use. So we're going to underline what? Yes, we're going to underline PV. We'll use only P and V. So we will write P2 V2 on the left side over P1 V1, also on the left side. Here's a mistake lots of students make with PV problems. And you might want to write this down, make a note for yourself. PV problems, the right side equals 1. A lot of students will write PV equals 0 and they get very confused. If these are all constant and you're dividing them by the same constants, a number divided by itself is just 1. So that is why the right side will equal 1. So we get P2 V2 over P1 V1 is 1, because this right side will equal 1. Now I'm going to isolate my unknown. What is my unknown? I didn't write that down over here. Let's write that. Oops. V1 equals what? What does V1 equal? So we're trying to isolate V1. And you should do that math right now. Don't just look at my answer. You should really not just be writing down what you see here. You should be trying these on your own to see if it is making sense as I go through them, especially when I'm doing the second example. Okay, so our V2, oops, I wrote V1 over there. That's V2. V1 was already given. We're trying to find our second volume. So V2 is P1 V1 over P2. Just isolating our V2. And then we plug in, and we get 168 milliliters. And that's it.